Okay, what I'm going to do today, I will try to inspire you as you have heard, we're supposed to give you inspirational talks for younger generation here. And I will try to inspire you to explore a very large family of two-dimensional materials, carbides and nitrides of earlier transition metals, which we call MXenes. M actually stands for a transition metal. Those are these red spheres in the models. X stands for carbon or nitrogen. Those are black dots connecting the spheres in the structures. And they can also have a variety of surface terminations as a surface. So this is a very large family of materials that come in a variety of flavors and colors that you can see. They have transition metals, so they can act as catalysts. They can change their oxidation state, those metal atoms, and store energy reversibly. And of course, they have many other properties, actually being true metals with a high density of state at the Fermi level. And this combination of properties naturally makes these materials attractive for electrochemical and electrocatalytic applications here. I'm going actually to divide my...
Yury, sorry to interrupt for a second. We are looking at your presenter mode. You might want to switch a little bit.
I did something wrong. What happens to me often here. Is it better now?
This is perfect, yes.
Excellent here. My apologies. So I mixed things up. So basically, let me also switch to the laser pointer to get finally everything properly organized. So I'm going to talk first about MXenes in general, energy storage. I will talk about MXene synthesis properties, that you understand what potential applications are possible. And then I will give a couple of examples of application of MXene in energy storage here. But maybe let me start even a little bit earlier than MXenes. Let me start with two-dimensional materials in general. And you don't need to be an expert in MXenes or graphene to know that this is a very hot family materials now. Graphene is definitely leads the pack, but there are many other materials available. Some of them are old, dichalcogenides like molybdisulfide or boron nitride or clays oxide. Some of them were discovered after graphene when attention was attracted to 2D materials world. Many of them were actually made from materials which are non-van der Waals, where there are actually efforts needed to create them, not just separate the layers. And MXenes are among those. But why is so much attention to the materials here? It's a very interesting family. One reason is, first of all, that they are 2D. So you can basically build them. You put them like building blocks, one after another, to create structures. You can combine materials with different electronic properties, semi-metallic, metallic, semiconducting, insulating. They have mechanical flexibility, optical transparency. If we think about future energy storage, wearable, transparent devices, Internet of Things, distributed, printed electronics, those are properties critically needed. You cannot take just a ceramic powder you say in current battery cathodes and process it this way. And also, by being two-dimensional, they have all their atoms pretty much on the surface. So the entire surface is exposed to environment. It's available to surface reaction, chemical, electrochemical, whether we're looking for a catalyst, electrocatalyst, or material for energy storage, there is no solid state diffusion required here. And these materials grow in numbers. There are a couple of hundreds 2D materials already made. And in 2011, MXenes entered the scene first slowly and then they started accelerate quickly. They're really on the rise now with more than 30 stoichiometric compounds between these M metals and carbon and nitrogen available. A dozen of surface termination. I showed the first one here, like oxygen, OH, fluorine, chlorine, but chalcogens, halogens, other have also been shown. Bromine, iodine, tellurium, sulfur, selenium on the surface. There are more than 100 stoichiometric simple structures possible. Multiply by 10 different surface termination, you get more than 1,000. Take solid solutions, you get infinite number. And particularly, if you look at this review article published about a year ago, at least as of 2018, 2019, roughly 50% of all papers published on MXenes dealt with energy applications of MXenes. Naturally, this was the first area where we started to use MXenes after discovery of this material family, and which has been explored by now pretty intensely by hundreds of research groups around the world. Let me take a step back again and discuss why we care about nanomaterials in energy storage. You hear all the time from media that we need batteries, car batteries, for example, that will charge within minutes. We talk a lot about wearable internet, Internet of Things, transparent energy storage window, and other stuff here. None of this is possible if you use conventional bulk materials. You cannot make them printable flexibly here. If you have solid state diffusion, you won't be able to charge battery within minutes here. And this is a review article we wrote with a couple of colleagues, Yitsui Xinliang Feng from Dresden. He actually just became a director of a Max Planck Institute in Germany. And Katya Pomerantseva and Francesca Bonacorso from Italy here, which we wrote about a year and a half ago, showing kind of this futuristic, forward-looking view of how nanomaterials can be used here. And if you work in the field of energy storage, you're certainly familiar with these plots, which we call Ragone plot. This comes from our recent paper with Patrice Simon, published last November. Think here, it shows specific power versus specific energy for different materials here. And what you will see is that batteries definitely store more energy because they use redox processes, transfer of electrons. Electrochemical capacitors or double layer capacitors, supercapacitors, ultracapacitors. So those are pretty much all the names for porous, high surface area carbon, which store charge electrostatically. They can be charged very quickly. This line shows actually time scale. It can go to milliseconds, but with much less energy stored. So how can you get at that point where you can charge a battery of your electric car within 5 minutes or so? You need to store as much energy probably as earlier as in lithium-ion batteries, but you need to do it actually orders of magnitude faster to get to this point. How to achieve it? First, it's obvious we need materials where there is no solid state diffusion. So we need nanomaterials, materials with high surface area, like electrochemical capacitors, electrochemical accessible area. We need materials which will have redox like battery materials. Moreover, what does it mean charging batteries say quickly? It means that you need to run a high current through this battery. So you need materials which will have high electronic conductivity. Remember that even activated carbon used in electrochemical capacitors have conductivity in, say, tens, maybe 100 millisiemens per centimeter. Actually, very moderate. Graphene, nanotubes, go above, reducing graphene oxide, 2000 Siemens per centimeter. MXenes can give you 10 times more, being real metals, having high density of state at the Fermi level. So what we're trying to do in our work, we're trying to control transport of ions in electrons in electrode materials and redox reactions like surface redox of transition metals to be able to balance energy and power and move in these directions that we can have high energy, high power energy source solution here. And we are trying to use MXenes for that purpose here. And again, to remind, those are materials made of these transition metals, carbon, nitrogen, and a variety of surface terminations here. They produce from max phases, but I will not really focus much on synthesis today. A colleague of mine, Professor Michel Barzoum at Drexel, is really the father of that field. This is a large family of layered ceramics, which you can look at as transition metal carbide and nitride layers bonded by layers of this A element in blue in this periodic table. But these bonds are strong, those not van der Waals bonds. So we have to etch monatomic layer out of the ceramics to break apart the structure. And then we can produce titanium 3C2 was the first one, but also many other carbides and nitrides of materials. And since they have now a transition metal on the surface and aluminum, say, or silicon or other element is etched away, transition metal won't remain unterminated. If you use etching in aqueous media, we will get oxygen, OH, or fluorine, HCl, chlorine from the acid. If you use molten salt, you can get other surface termination like halogens here. But the idea is we get structures with those surface terminations. Moreover, we can make not only pure structures, we can make atomic sandwiches where one element like moly is on the surface, another element like, for example, titanium is squeezed in this sandwich in the middle. It's also possible to make structure with alternating atomic columns of different transition metal, for example, moly and yttrium or scandium. And if you remove yttrium or scandium, you end up with ordered divacancy MXenes, structures where monatomic columns of one element are missing. So you get the idea. We can really do atomistic engineering at the best level. And to take it further, we can mix different atoms in solid solutions, in both actually X layer, carbon nitride, but also in M layer. For example, you can imagine catalytic material with, say, moly or tungsten atom surrounded by titanium atom, a kind of single atom catalyst. So, and you can pretty much create an infinite number of compositions. But the research goes on. About a year ago, we published this paper in ACS Nano, showing that we can make materials with actually 5 layers of transition metal bonded by 4 layers of carbon, moly 4, vanadium, C4, thicker structure. And transition metal inner layers gives electronic properties, electronic conductivity. Free electrons of transition metal provide for this conductivity. And the outer layer, terminated by oxygen or OH, gives this reversible redox. So we basically have a material which is conducting like metal. And keep in mind, graphene even is a zero band gap semiconductor. But those materials have high density of state at the Fermi level. And at the same time, its surface looks like a surface oxide or hydroxide. So you can run the same, say, electrochemical reaction like with oxides. And they can have conductivity like a 3 orders of magnitude higher than activated carbon using supercapacitor, or at least an order of magnitude higher than, say, reduced graphene oxide. It's very important, again, for high power applications. But these oxide-like surfaces give also easy processability from aqueous solutions. and they are electrochemically active. Otherwise, these flakes look like flake of many other 2D materials. You see, for example, a hexagonal imprint of the structure. Those are single crystal. This is a single layer, single crystal titanium 3C2. This flake is about 20 micrometer in length. And you can pack thousands of those flakes in this type of structure similar to, say, graphene or graphene oxide paper. And it's all possible. There's also one more important feature of those materials. There are more than 200 two-dimensional materials which have been reported. Only a handful of those can be made in any significant amounts. Graphene, molybdensulfide, boron nitride, some oxides here. MXenes are produced by wet chemical etching from ceramic precursors, MAX phases. This is a reactor which was designed by Materials Research Center in Ukraine for us. We have a couple of reactors of different volumes. We can make up to 100 grams per batch. In industry, there are reactors already capable of making kilogram per batch. Fundamentally, it should be possible to make a ton of material per single run in a reactor. And what you can see here, it's about 50 grams of titanium carbide MXene, this powder, produced from this ceramic precursor. And you can take this material, basically we etch, we delaminate material, we wash it, we filter material, we get powder. Or we can simply dissolve it in water. This is a 1 liter bottle of solution of MXene. It's dark, probably about 10 milligram per milliliter. We have a 20 liter, like a 5-gallon tank standing, filled with this solution in the lab here. And what is also nice, you can process it from aqueous slurry. MXenes have oxide or oxygen or H group on the surface, so they are hydrophilic and negatively charged. You can concentrate, make, for example, liquid crystalline solution and use Dr. Bley method to produce this film. It's just 1 micron thick and it has strength higher than aluminum foil and about 15,000 Siemens per centimeter. No additive, no nothing. You just spread the solution by Dr. Blade, dry it, and you get this film. Considered to be electrode current collector. And I will talk at the end of my talk a little bit about MXene current collectors that actually suppress growth of lithium, potassium, sodium dendrites here. But you can also use any other processing method. You can print them, inkjet print, 3D print, draw with MXene, spin coat, spray coat, pretty much anything you can do with aqueous colloidal solution, including making this type of films by simple processing. And again, I'm stressing this because, say, if you take a graphene oxide, you can process it from water. But then you need anneal it. You need to reduce it to produce reducing graphene oxide, which is conducting because RGO, conductive GO is not. Here, you don't need anything. You take many other materials. You need to add surfactants to carbon nanotubes or graphene to be able to disperse them in water. No additives needed. No binder, no additives, no nothing. Moreover, you can use MXene as a binder. And all this justifies and motivates electrochemical applications of materials in energy storage. So why are they attractive? First, as I mentioned, they are highly conducting. They're actually probably the most conducting of materials used in energy storage. They, at least titanium carbide MXene. But their surface looks like transition metal, oxide, hydroxide, fluorides. Actually, oxygen-terminated surface predicted by DFT to be the best one for a variety of energy storage applications here. And these layers of transition metal with electrons available for conductance make it through metals, allow fast transport for electrons, and galleries between the layers allow for transport of ions. I'm going to give a couple of examples first on aqueous systems. We start with intercalation water just after synthesis, and we have protons there. But there are, of course, possibility to use organic electrolytes, ionic liquid electrolytes, work with lithium, sodium, potassium, and other elements. And what we do in my lab, we first do electrochemical characterization, cyclic voltammetry, galvanostatic charge-discharge impedance, electrochemical impedance spectroscopy. And then we look in situ, studying the mechanisms of processes to understand what is going on when ions go in MXene. Are there redox reaction? Is there charge transfer? And with this, we can basically understand what is going on with the material and learn how to control it. Because keep in mind, we have dozens of simple compositions. We have variety of surface terminations. We have many more compositions that are possible in solid solutions. So our challenge is to select which one is the best, how to control the surface termination, how to design architecture. We can make freestanding films. Actually, MXene don't need current collectors because of this conductivity for testing. But we can also use multi-layer powder and prepare electrodes in a conventional way using, for example, polymer binders or just slurries on a current collector. Both are possible. And also in aqueous system, we use as counter electrode, usually activated carbon and reference electrode and 3-electrode cell, experiments from which I'm going to show it to you now. And what we find there, if we take some of the salts, for example, sodium sulfate, we get cyclic voltammograms, which is perfectly rectangular, very much resembles that of double layer capacitor carbon. So we assume probably no redox. But in a protic electrolyte, you will see these peaks, which are electrochemically reversible, but shift slightly and separation increases as we increase the rate here, getting high volumetric capacitors. So first message is different ions give you different processes here. Moreover, if you look more carefully and take thin film electrodes and charge and discharge it in sulfuric acid solution, it's very interesting. We get a double layer envelope and we get this broad reversible peak. Moreover, up to rates of maybe like 5 volts per second. It's electrochemically reversible. So separation is like less than 20 millivolt between the peaks here. So we get a redox, and I don't have much time to talk about it, but it's basically we switch between oxygen and OH as we go in voltage down to -1 volt, and we pretty much transfer an electrons to oxygen terminated titanium atom by doing this. As a result, we can get very good capacitance values in spite thicker and heavier materials than carbon. And if you look volumetrically, we can go to about like a 1500 farad per cubic centimeter because again, high density of MXenes here. But if we take different ions, we can observe very different behavior. For example, some ions like aluminum or magnesium, lithium will bring water in when they intercalate between MXene layers. Some other ions like tetraethylammonium will push water out. Some ions will hardly change interlayer spacing when they go between MXene sheets. And understanding and appreciation of these factors is important because ions that go inside even with water, but come close to the surface of MXene, they are able to polarize surface of titanium or other, again, it can be moly, vanadium, niobium, other transition metals. I'm just giving an example of the most common MXene here, and definitely lead to more significant charge transfer. As a result, larger capacitance values. It's an inverse of a distance of cation to oxygen of the surface in this case here. So it means that if you even take different ions in aqueous solution, you can get different results. Same things happen in organic electrolyte. This is now lithium TFSI in DMSO, acetonitrile, and propylene carbonate. And what we found when we studied this system, the results were very anti-intuitive. Highly conducting acetonitrile solutions that in a supercapacitor, conventional supercapacitor, carbon supercapacitor, should give the highest performance, actually got the lowest capacitance area under cyclical thermogram. And propylene carbonate with an order of magnitude lower conductivity gave us a much larger cyclical thermogram. So what is going on? What we found is that in case of DMSO acetonitrile, lithium ions go between the layers with solvent. DMSO at least have them both on the surface adsorbed and mixed inside, so there is a fast transport. In case of acetonitrile, lithium ions go to the surface of MXene, but solvent molecules separate layers, hurting electronic transport and also taking space and also leading to like a brazing of the electrode expansion contraction. But in case of PC, there is a complete desolvation and lithium ions go between the layers without solvent, giving more energy stored, larger charge storage, but also no change in the spacing as we cycle the electrodes. It's totally stable here. So a message from this is that whenever we take new materials, it's not easy to introduce them in energy storage system. We need to understand the effect of ions and solvents on the behavior of this new material system and select them appropriately to achieve the performance. What is also important, you can use MXenes as active materials in supercapacitors, batteries, and in also hybrid devices. But a lot of improvement can be achieved by also using them as passive materials or both passive and active material, using them as current collectors, using them in a binder, for example, for silicon, tin, or other materials with large volume expansion, poor conductivity, but high capacity, large energy storage ability. And you can use them actually instead of polymer, even for activated carbon in electrochemical capacitor to accelerate and improve charge storage here. And of course, this application start finding use in many different systems, for example, in lithium and sodium sulfur batteries, where MXenes can be used as host for sulfur. They strongly adsorb polysulfides. Linda Nazar was the first one to show this behavior, and many other groups, including our group, followed up. They can adsorb polysulfide, they can catalyze transformation. They can also be used as films and separator to prevent polysulfide transport to anode, and also as support for lithium or sodium growth on an anode, replacing copper or aluminum here. And you can see, for example, stable cycling of a battery. This is not our work from the published result with MXene electrodes and very good Coulombic efficiency over about 800 cycles and moderate loss of capacity here. But what is also important, whenever we have new materials, we need to think where they can make real impact and difference. And if we talk about two-dimensional materials, nanomaterials, naturally those are flexible devices, printable devices on a chip, or wearable devices here. This is where you need to consider those materials here. And if you talk about this type of a transparent, for example, conducting films to replace ITO, uses current collector, or battery electrode, you also can think about extra benefits. For example, suppression of lithium dendrite. And this is a paper with Professor Yinjin Wei and Alex Gao from Jilin University, showing stable cycling over actually 600 cycle here of lithium, and uniform film of lithium because of planar growth of lithium, not dendritic growth on the surface of MXene here. So there are many other applications which I simply cannot cover in this short talk. What I want to give you just a flavor of the field. This very large family of highly conducting materials with redox active surfaces, with a variety of transition metal on the surface, with several different structures, with a different number of layers and different arrangements of atoms there. And of course, they already are being explored in many different electrochemical applications here. From electrochemical capacitors, lithium, sodium-ion capacitor, to pretty much all kinds of batteries, and so on and so forth here. To electrodes, brain electrodes, implantable devices, electrochromics, and electrocatalysis. There are many, many other applications, but I have just a couple of minutes left, so I need to wrap up before my time is up here. If you want to learn more about electrochemical application of MXene, this review article in Nature Materials is a good starting point, but keep in mind, it is getting dated. There are several other reviews from other groups published more recently. And of course, there are many applications beyond energy storage I mentioned today. There are applications in electrocatalysis. For example, Moly2C is an excellent hydrogen evolution reaction catalyst. You can also do photoelectrochemical catalysis because MXenes are plasmonic materials. You could see these different colors for different MXenes in the beginning. About 50% of all publications today deal with a single material, titanium 3C2 MXene. TX stands actually for surface termination. Sorry, I didn't explain it from the beginning, and I used it in many slides here. It's a great material because it's made of earth-abundant elements. Titanium, carbon among the most common elements used, non-toxic, biocompatible. That's why implantable electrodes and like a photothermal therapy or dialysis are possible with this. But for electrochemical applications, moly, niobium, vanadium may be able to transfer more electrons, do better redox. Definitely, they are better catalysts for majority of reactions here. So there is a lot to explore here. And of course, we do this exploration not alone. This is my very international, great research group. Those are people who have done research I showed to you today. This is actually a picture taken more than a year ago, before pandemic, at my flat. We collaborate with many people at Jackson University in the United States and around the world. This is just very, very small subset of collaborators here. Also, much of our electrochemical energy storage research has been supported by the Department of Energy, by First Energy Frontier Research Center, where we work with colleagues from Oak Ridge National Lab and a bunch of universities on MXenes here. And with this, I am going to stop. I think I just have 2 minutes left for questions. Thank you very much for your attention. I will be glad to answer questions, if any.
Thank you very much, Yury. It's just a fascinating talk to hear about the genesis and growth of MXenes. So this workshop is being broadcasted over multiple platforms, reaching over 5,000 audience right now. But we're going to open the floor up for questions. For those who are here, feel free to unmute yourself and ask questions. And as I receive the questions from the other platform, I will pass them on. Anybody? So I do have a kind of more general question, Yury. It seems everything is ready, right? You have these excellent properties. I'm talking about energy storage. It seems the synthesis have been scaled up. What do you think will be the next roadblock to bring MXene into the real applications or devices?
Well, there are many. We always need to be realistic. There is a long way from initial discovery and demonstration of feasibility to practical real-life applications. Kilogram quantity seems to be a lot, but how many kilograms do we need for a Tesla car battery? So we anticipate that initial application will be in small scale, small size devices, in catalysis, in flexible electronics, and so on. We definitely need to learn much, much better how to deal with these materials. And we have overcome a couple of, for example, major obstacles, how to scale it up, and second, how to improve stability. We currently can keep slurry of two-dimensional flakes solved in water at room temperature in case of titanium 332 MXene up to a year. For MXenes that are considered to be the least stable, like V2C, for a month at least. And in a film, they can be basically used for a long time. Even in sulfuric acid, you can cycle it for a year and basically take a device which has been stored and recycled here. But there are many more applications. We don't still understand exactly the mechanism of intercalation of many ions here. We learn how to truly get multivalent ions between the layers for the batteries. And we're trying to find where is this sweet spot for applications here. Where will be the first application? And actually, currently, electronic application, communication, antennas, electromagnetic shielding seems to be the entry point maybe for MXene. Biomedical, medical electrodes, when MXene simply replace gold or platinum, performing better than those here. And then we need to grow the volume because it's again economy of scale to decrease prices here. So I think there is a long way to go, but there is plenty of room for discovery because there are so many materials, and it's a blessing and a challenge. I did not talk today about modeling simulation at all, but tremendous amount of work has been done. Much more is needed. We really need guidance from artificial intelligence, which materials to create, how to optimize it for different type of ions, different type of electrolytes in the batteries here. So I think we just like opened this area for research and applications. And now it's up to research community to enter and benefit from this wealth of 2D materials available to them.
That's great. I agree. This is indeed a very versatile and fascinating material platform. Thank you again, Yury.
It's my pleasure.
For one, for a question.
Yes.
Yeah, Yury, it is you have the two-dimensional materials, and my understanding, the edge will be the most active reaction site. How do you control those edge? And another question is, for example, like the application you have for battery supercapacitors, you want the layer to grow vertically, not in this way. Mm-hmm. Is there any thought?
Well, basically, you are right about many of these things, but there are a couple of things here. One, for example, in electrocatalysis, it has been shown in HR that unlike dichalcogenides, actually the entire surface is electrochemically active. However, edge is a challenge. This is actually where oxidation in water or in air starts. So what we worked on to develop process that basically keeps edges straight, which keeps material stoichiometric. There are fewer points where degradation starts here. So control is important, very important here. Second, I really did not talk at all about architecture design today. We make this material as really like a flakes powder, but 2 years ago, we published a paper in Nature with Professor Shu Yang from UPenn, from Material Science and Engineering Department, showing that by using this liquid crystalline approach, we can make a film in which flakes are pretty much vertically oriented. And as a result, we got up to 200 micron like a thickness independence capacitance here. So yes, electrode architecture design is again another important task when you deal with 2D materials. One good thing is here, people have done a lot of work on graphene and other 2D materials by now. And if you're entering the field of MXene, you don't need to reinvent the wheel. It's very helpful to build on existing knowledge for other 2D materials on processing and actually apply it to MXenes here. But all these issues are valid and important.
Great, thank you. So for the sake of time, we'll move on to our second speaker. Thanks again, Yury.
Again, thanks everyone and goodbye. Let me stop sharing my screen and go silent.